Welcome back. In this lesson, we'll talk about magnetic anisotropy. As we described earlier, magnetic anisotropy is actually a very interesting concept in the sense that it's very important for actual industrial and life applications. As we mentioned in our last lesson, when the system becomes long-range ordered antiferromagnet, the moments are actually aligned along a particular direction. And such a direction turns out to be extremely useful for applications. Many years ago, people have utilized a compass to actually determine the direction of the Earth of the field, essentially determining which direction is north and which direction is south. Of course, at that time, people do not know the microscopic origin of the magnetic compass. So this is actually the fundamental concept of magnetic anisotropy. And in the case of a compass, essentially the moment or the magnet is actually aligned with respect to the external Earth magnetic field. In the case of the Earth, typically it's the south and north pole. So what do we actually mean by magnetic anisotropy? Magnetic anisotropy actually means that when the magnetic moment is aligned on a particular direction, actually saves a lot of energy. And details of that will be derived in a separate light bulb discussion section. I will present a much more detailed derivation of why this equation arises. In this particular equation, K is what we mean by anisotropy constant, which has a unit of joule divided by a cubic meter. And then you have a sign, and phi is the angle between ms and the EZ axis. And EZ axis will be the axis of the moment direction when you have no external disturbance. Essentially, this phi determines how much angle you have between the EZ axis and your ms. Let me give a very simple version of a derivation of magnetic anisotropy in a very simple cartoonish type of picture. So magnetic anisotropy is a bit hard to understand by itself. But if you think about yourself as having a simple dipole, we all know what is dipole composed of. A dipole is composed of a negative charge and a positive charge. And then we think about a dipole essentially as a P, which is proportional to the size of the charge, and then proportional to the distance between them. So when you think about a simple dipole in the presence of an external electric field, what will happen? Let's say in this particular case, our electric field is along the horizontal direction. And then we have this dipole inside external electric field. Of course, the dipole would want to be aligned along the field direction. Let's say if the dipole has a positive charge as red and negative charge as blue, and the dipole would like to flip around the field direction so it minimizes its energy. And what this actually means is that there's actually a torque present onto this dipole when the dipole is not along the external electric field direction. And then the amount of torque is going to be proportional to this, which is related to the angle of the sky. And then you can actually estimate the potential energy of a dipole in the external electric field. And based on this external electric field and its dipole relationship, you can actually calculate the energy dependence of the potential energy as a function of a theta, or as a function of a phi angle with respect to between the dipole and the external electric field. And the magnet, a simple magnetic anisotropy in the case of a magnet works in an identical way. We will derive this a bit more detail in our light bulb session. So what is magnetic reversal by coherent motion, by coherent rotation? As we discussed in our last lesson, when we apply an external magnetic field onto a ferromagnet, you can have cases in which the magnetic field can be gradually changing the domain wall, either reversibly or irreversibly. So this process essentially starts from when the field is at 0. As you gradually increase the total external magnetic field, you gradually align the moment along the field direction. At the maximum field, when you completely saturate the moment, and then the moment will be aligned on the same direction. And then if you turn the magnetic field, initially, of course, the field is along this direction, And then when you suddenly start to turn the field along the other direction, and then your magnetization does not come back to this, and then gradually form a hysteresis loop, as we described in our last lesson. And the size of the hysteresis loop essentially is determined by coercivity of the magnetic field, or essentially the magnetic properties of the particular material you're dealing with. In the case of a very simple soft ferromagnet, and this hysteresis loop essentially does not occur, meaning that anytime you magnetize it, it fully magnetizes it. When you reduce the field, it becomes zero. But in a lot of hard ferromagnet, and you have this very large hysteresis loop, and this is essentially what we use this property to determine the system as to become a permanent ferromagnet. So the energy for this is related to this equation. We'll discuss a little bit in our light field, light bulb discussion, and this is what we call the anisotropy field. So typically, magnetization reversal by coherent rotation means if you're gradually turning on the external magnetic field onto the system, essentially you initially increase the total magnetization, and then finally you saturate. And this anisotropy field is what we call the magnetization reversal. This is what we call the anisotropy field that's needed for the system to become totally ferromagnetic magnetized. And the typical picture is shown, in this figure. So what is the microscopic origin of magnetic anisotropy? That means, why does a ferromagnet prefers a particular direction alignment when the system spontaneously magnetizes, meaning the system changes from a paramagnet to a ferromagnet? Physically, there are two reasons for that. One reason is what we call the so-called dipolar interaction. This means you have a dipole-dipole interaction. Physics-wise, you can think about this as follows. You can think about each of the magnetic ordered moment along each atomic site as a simple dipole with a north and south pole, very much analogous to the electric dipole that we discussed in our earlier slides. And then the dipole-dipole interaction sometimes can make sure the system actually prefer a particular direction in the system. And the other important factor for the origin of magnetic anisotropy is what we call spin-orbit coupling. And this is the atomic physics. So if you think about the composition of an atom, the composition of an atom is composed of a nucleus and then all the electrons around the nucleus. When you stack those electrons around the nucleus, you can have different states. Because of a Pauli's exclusion principle, one S state, for example, can only take at most 2 electrons. As you gradually have an atom with more electrons than 2, then you have to stack more orbitals. For example, you stack orbitals S, and then you stack more orbitals on the outer range, and then your angular momentum will no longer be 0. And then in this case, you can possibly have spin and then the orbital interaction. And spin and orbital interaction is atomic interaction such that it prefers a particular direction in the system. And this actually determines, in some materials, a preferred direction, and this is the direction we call the EZ-axis direction. So because of these two physics, one can have a magnetic order, but the order typically along a EZ-axis direction.